Hello everyone, welcome back to a new episode of Advent of Code. We, in the last episode, left off a bit stymied as to how to start on day 3 and had some infrastructure work to do before I could even really start coding it. And I did not have a clever solution in mind. I, figured out a way to brute force it. And, well, long story short, I did all that. I ended up solving this one off camera. I'll give you guys a tour of the solution momentarily. But it was just like, for numerous reasons, it didn't end up getting a live recording of that. Made some technical problems with the recording. Also, it just was not very good footage because it turns out to be like a kind of drudgery sort of solution. And it was hard to explain all of that while writing it, blah, 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 blah. So, all of that said, hey, shouldn't I have switched, there we go. What have I done since the last episode? Well, first of all, I have written this program, but before I tell you about that, a detour into Yak Shaving. To get Intero running, I had to upgrade my Emacs version. This had some ancient version, 23 dot something maybe, or 24.3 I think. Many years old. I couldn't figure out how to get Intero running on that old version, and I couldn't get the new snapshot version of Emacs working at all, and I couldn't get a copy of this version, which I knew I could get working in Intero on. I couldn't find one anywhere. So I had to go compile Emacs from source. Blah. But it turned out not to be so bad. It took 20 minutes or something. And then, magically Intero started working. So that's a success. We have Intero now. What else happened? I put my Git repo on GitHub, finally. That's the thing I kind of meant to do, but hadn't done at the beginning. So now it's there on github.com/amalloy/something, AOC-2017, if you want to go have a look. What else did I do? Sure. So let's go look now at the program, and in particular, something that I had to do before I could get started was I needed to know how to add some libraries. And this is not very hard. Basically, the Cabal file is the project definition, and I had to add transformers and containers and go look on the website to find some reasonable versions for those things. I don't know. I said these are versions I'm okay with. I don't really know why, but they're close to what's current, so it worked out. The interesting thing is there's a whole bunch of Haskell code here, right? We have 79 lines. Oops, that's not the button I wanted. Is it Control C? Control L? No, that's a different thing. There's some button somewhere. XL? No. I don't know. There's some button you can push that will count the lines in the file, and I don't remember what it is anymore. Doesn't matter though. We don't really need to do that. Who knows? Okay, so what did I do? I'm going to try to give you guys a whirlwind tour of this so that we can get on to day 4. Because I don't think this is a very good program. I'm not at all terribly proud of how I did this. It seemed like a very brute force approach of doing every little thing rather than finding some more elegant way to sort of abstract over it. Basically, I said, let's start by defining some types. We want to walk our sort of cursor in a spiral around the center. So at any given time, we'll be pointing in a direction along that spiral, and we'll be at some position on the spiral. So we need types for that. A direction is any one of these 4 things. A position is just 2 ints. And furthermore, I wanted to do this in kind of a stateful way where we can pretend that we're modifying some state in place. And to do that, we need a single type that describes all of the state that we'll want to track. And so I called this a map grid. And I said a map grid is a grid of, well, a thing called a grid, consisting of an int, the current number we're sort of putting down, how far along in the list we are in the spiral, what direction we're currently pointing, what position we're currently at, and also a hash map from position to integer, what value is at this position. So these are all the types I ended up needing. That's nice. We didn't need too much complicated stuff. but we needed a few things for how to work with those. Since we wanted to turn left, I wrote a function that takes a direction and returns another direction. And this uses Haskell's pattern matching. I can just define a function in 4 parts by giving 4 equations for it. And Haskell just, when you call turn left on a direction, it checks like which of these cases applies to the input and uses the corresponding right-hand side. So if you call turn left on up, you get left, and so on. And likewise, a function that says, given a direction you're pointing and a position you're currently at, what should be the new position if you were to walk forward 1? And this is like, you know, we pattern match the position into its y and x components, and then we, depending on the direction, we add or subtract 1 to y or x and return a new position. So this is all like fairly mundane and laborious. I'm not going to get into it too much, but like something that had to be done. All of the real interesting work in this solution is in the function spiral. Now here's where we get into the stateful computation that I was talking about. We want... by the way, this is the final solution that includes part 1 and part 2. The part 1 only version was somewhat simpler, and I could go back and show it. I do have it in Git, of course, but I don't think that that's super instructive. We'll just look at the more complicated one. Basically, Spiral, ignore the arguments for a moment. They sort of configure how Spiral works in some way. But really, at its core, what Spiral does is it is a stateful computation where the state that it can save and modify is a map grid, and the type of value that will be produced by the stateful computation is of type A. Well, what's the deal with A? A is a type that the caller gets to choose by specifying the result function. So Spiral takes 2 functions to configure it, one of which is, given that you're standing at a point, how do you choose to label it? And the other is, how do you decide when you're done, and what is the result if so? So label is a stateful computation working on the same map grid that produces an int, what should go here. And result is a stateful computation on the map grid that might, this is maybe, it returns either a value of type A, if it's decided you're done, it gives you the result, or nothing, and says, nope, you're not done yet, keep going. We'll get into more about how maybe works in some future puzzle, I'm sure, but again, I sort of want to just give a whirlwind tour of this rather than describe it in absolute detail, because this is not, I think, a great program for a third. This is not the third Haskell program you should ever read, I guess is what I'm getting at. But the idea of this algorithm is basically you ask the label function, hey, what should I label the next node? And then you do that. You modify the map you're working with to write the new label to the current position. And then we ask the result function, are we done yet? And if so, then we just produce that as our output. Otherwise, we try turning left and see if that's already been labeled, and if not, we go that way, and if so, then we go forward. So that's sort of how you trace out a spiral. And then we just do that forever until the result function says that we should be done. And we have this little solve function here, which is just basically a wrapper around Spiral that sets up the initial state of the stateful computation. It's really all it does, and takes the output of it. And so part 1 and part 2 are both just different calls to this solve function. Part 1 uses a labeling scheme where the label is just, goes up by 1 every time. It's whatever index you're working on, that's what you should label the thing. Very simple. And the result function is like, did you get to the number you were trying to get to? If so, add up the coordinates you're at, and otherwise that you're not done. And so that works. You can see when we do it, it's a bit slow because we're tracing out a pretty big spiral. Actually, we don't have to wait. We can go up and look at the previous output, right? Run GHC. There we go. So 438 is how far away this thing we're looking for is. Fine. So then we go over to Advent of Code, and we give it the answer, and it says, hooray, you were right. Part 2 is, it made me glad that I did decide not to do this on pen and paper, and instead actually produce the spiral. Because I don't know how I could have done part 2 on pen and paper. Basically, the way that this works is, rather than just setting the values in order, 1, 2, 3, 4, 5, as you walk through the grid, you initialize the middle part of the grid to 1, and then you walk in the same order you did when you were labeling them increasing. But you set each cell's value to the sum of all the 8 adjacent squares to it. Treating empty squares as 0, right? So they're saying that this 1 here, that's the first value. This one is where you walk to next, and at the time you get there, only one adjacent node is filled in, this one, so it's 1. Now you walk up here, and there are 2 adjacent nodes, these 2. You add them up, it's 4. You get here, and the 2 and the 1s, so you get a 4, and so on, right? So they describe this, and then the question is, what is the first value written that is larger than your puzzle input? Okay, so that means part 2 needs some slightly different... It's another call to solve, but with just different label and return functions. The label function is basically like a rather long-winded way to say, to label position P, look around P in all 8 directions and add up everything you found. I won't go into great detail on how that works, but that's what this function does. And the result function is, well, read the current value read the current position from the state and look up that position in the map that's in the state. And if it's greater than the goal, then return it, and otherwise don't return. And so this works, and we get the final answer. So like I said, I think this is very brute force, not elegant at all. I'm sure there's something better. And it also introduces, my solution to this introduces way too many concepts for me to go over it all in great detail. So this is really going to be all you're going to see of day 3 at this point. But this means we have plenty of time for another day. Oh, wait. How do I go back to my calendar? Here we go. Let's move on to day 4. And I had a peek at the next upcoming puzzles to see if there were any that I wanted to do off camera again. But this one, at least, is very simple, short anyway, and we should be able to do it on camera pretty comfortably. So day 4, high entry passphrases. A new system policy has been put in place that requires all accounts to use a passphrase instead of simply a password. A passphrase consists of a series of words separated by spaces. To ensure security, a valid passphrase must contain no duplicate words. The system's full passphrase list is available as your puzzle input. How many passphrases are valid? So here's our input, and it's got just like a lot of lines, and each line has a number of words, and we're supposed to say how many of those lines satisfy the condition that each word on the line is unique. So we'll just grab this and move back into day 4. Paste. Good. Fat. Rude. Huh. Okay, so obviously these are not very memorable passphrases, but I don't know, maybe it makes sense if you're an elf, who knows. So let's get started on implementing this. I don't think it should be too difficult, at least part 1. So let's go look at AOC, up to 04, source. Oh, by the way, I mentioned that we have Intero, but I didn't show you how it works. Why did I want it? Why is it so great? So we'll go back and look at this. I almost forgot. You guys got to see the code. Here, I'll show you the I was just remarking that this guy has a password that says fat. Okay, fine. Still, as I said, I think I said in some previous episode that I'm still not in the habit of remembering to switch windows, since I usually play single window games when I'm recording. So it's easy to forget. But I'll try to keep an eye on it. I really hope I don't. It's a big pain if I've gone on for a long time while you guys are looking at the wrong window. It kind of sucks. Okay, so what's the deal with Intero is, well, one, we can have a REPL inside of Emacs that just like automatically has all of the code from our thing, which is great. I'm not going to use that right now. But another thing that is quite useful is you can ask Intero at any time, hey, what is the type of a thing? For example, what is the type of this pause apostrophe thing? It's of type position. I didn't ever tell Haskell what the type of pause is, this local, like you would have to in, say, C or Java or something like that. When you declare a local, you have to give it a type, and then if the type's, and then you put values in it, and those values have to be of the right type. Haskell, you can give things types, and it's good practice to do so, especially for like top-level values. But for locals inside of functions, people usually don't. And the compiler is smart enough that it will tell you exactly what type everything should have. So I can say, what is the type of pause? And it says down in the bottom left there, it's a position. What about turn left? It's a type direction to direction. So can I ask about flip const, by the way? I guess so, yeah. Flip const is of type int, int, int. Cool. So it's cool that we can do this, ask about types of things. And it also like has context-aware autocomplete, which is handy. But anyway, so let's move on and work on day 4. So what we want to do is write the same thing we've been doing. Main equals interact of show dot part one composed with map words lines. So I think we're going to want to turn, just like we did before, going to turn the input string into a list of lines and that into a list of lists of words. And then we'll do this part1 function, which is going to do something. So part1 is a function taking as input a list of string and producing as output an int, right? We're supposed to say how many of the passphrases are valid. Part1 actually we could probably write part1 of part1 equals length composed with filter permissible, where permissible what function am I thinking of in Haskell? Is there something like distinct? Do I still have Hoogle? Yeah, here you go, Hoogle. So I have a list of things that can be compared for equality. I have a list of such things, and I would like to have back a different list of them. So there's nub, like that's a thing I could do. Get a unique version of the list. What if I were to say I want back a Boolean instead? Is there like a distinct question mark kind of thing? Like, are they unique? I don't see any evidence of such a function. Anything in base, please, especially? More results? Yeah, none of these look very promising. Okay, so that probably doesn't already exist, but it's fine, we could just use nub. Permissible of x's equals x's equals nub x's. Yeah, that seems okay. The idea is a passphrase is permissible if it is equal to nub. So nub takes a list and gives you back a list of the distinct values in the input list. And if those two are equal, then all the values must be distinct, right? This is not terribly performant, but it's fine. We have small lists. So that's our permissible function. And part one is basically filter all of the passphrases, keeping only the ones that are permissible, and get the length of that. So I think this really ought to be just fine. And so let's try it, right? Run GHC. Variable not in scope. Oh, it's in data.list. Okay. Import data.list nub, please. There we go. We got a number. So probably the right one if I had to guess, but we'll see. That's the right answer. Okay, now what's part two? It's going to be harder, I'm sure, somehow. Yet another system policy has been put in place. Now, a valid passphrase must contain no two words that are anagrams of each other. That is, a passphrase is invalid if any word's letters can be rearranged to form any other word. So this is actually quite easy. A very, very small change, and I will show you why in a moment. But first, git add day for part one. So really, how do you test whether words are anagrams of each other? There's a lot of ways you could do it. A lot of ways that perform pretty well. But one way that performs okay is to just sort all of the words and then see if they're equal to each other. Any two anagrams are the same when you sort them. That is, sort the letters within the word, not sort the words within the line. So I can really just do something very simple and say part two is another function from list is, like this, int part two equals part one composed with map sort. So take all of the lines of the that we're given, all the passphrases, and map a function over them. The function that we're mapping is another map sort, saying to sort each of the words. And I think this should be it, right? Like, let's import control.arrow like we always do, and just write part one and part two. And I think we ought to be all good here, right? Sort. Is that in data.list? I guess it is. Look at that. Perhaps you meant to add sort from the import list. Okay. Who knew? Sort. There we go. 119. So nice and easy, and I'm reasonably confident this is correct. That's the right answer. Great. So day 4, way easier than day 3 in my opinion. Maybe I missed something, but certainly was easier for me. Let's look at day 5. I don't know if we're going to do that one in this episode or not. A maze of twisty trampolines all alike. An urgent interrupt arrives from the CPU. It's trapped in a maze of jump instructions, and it would like the assistance from any programs with spare cycles to find the exit. The message includes a list of the offsets for each jump. Jumps are relative. -1 moves to the previous instruction, and 2 skips to the next. Start at the first instruction in the list. The goal is to follow the jumps until one leads outside the list. In addition, these instructions are a little strange. After each jump, the offset of that instruction increases by 1. So if you come across an offset of 3, you would move 3 instructions forward, but change it to a 4 for the next time it is encountered. For example, consider the following list of jump offsets. Positive jumps move downward, negative jumps move upward. These offset values will be written on one line with the current instruction marked to help us remember, but I have a mouse pointer, I can do it up here. So the idea is we start out here, and we jump forward by 0. Well, that didn't put us anywhere, but we replace this 0 with a 1. Next we jump forward by 1, and increase the number to a 2. We land here, on this 3. So we jump forward by 3, and replace the 3 with a 4. Now we're here. We jump backward by 3, but replace the -3 with -2. We land here on a 4, which jumps us 1, 2, 3, 4 outside. And now we're outside the program completely, and that's how we know we're done. And the question is, how many jumps does it take? So this took 1, 2, 3, 4, 5 jumps. Now, an array is a very obvious data structure for solving this problem. And Haskell does have arrays. Its sort of typical data structure is the linked list. All the lists we've worked with so far are linked lists. You can get arrays, and that might actually be the best way to do this. But there's also a cool data structure called a zipper, which is basically meant for a list that you have a cursor in and that you move around in, which sort of perfectly describes this problem that we have here. And that is sort of fits better in a functional language. Now, Haskell is flexible, and it'll let you use arrays, even mutable arrays if you want. I don't know how that works exactly. You have to be in some monad that like lets you do that stuff, but it certainly can be done. However, I think it would be fun to do this with a zipper instead. And I know that there are implementations out there somewhere of like a list zipper, which is what we would be using. But I think that this is a simple enough problem that I would rather implement my own, and it will be not so complicated. I think that I'll be able to explain to you guys sort of what's going on. It'll be a good exercise in looking at the various ways that Haskell lets you define data types in a little bit more detail than we did in the previous exercise. So I guess we may as well get started, right? Sure. So day 4. Oh, day 5. We're already on day 5. I should commit this, right? Git commit day 4 part 2. Did I accidentally commit anything I didn't want to? No, just the source file. Okay. So now, let's get started on day 5. So do I need to import anything here? Well, I'll want control.arrow eventually, of course. But let's define a new data type called a list zip. Let's call it a zipper. Whatever. A zipper of A. So we can have a zipper of any type, right? It doesn't have to be a list of ints. Ours will be, but we might as well define a more general zipper that can hold any kind of type. So a zipper of A, there are kind of 2 ways you can have a zipper. Right, so remember the idea of a zipper is it's kind of a list, but also with a context element that you're pointing at. How do you... I might want to look this up, huh? Haskell list zipper. Look at that. It exists in data.list.zipper. Maybe I should actually use that instead of defining my own. Let's see what this is all about. So it's a zipper. It's a zip of 2 lists of A. So what exactly are those? Focused on the first element. So it's basically a list with a focus point where you're currently looking, and it's implemented as all the stuff before the focus and holding 2 different lists: the stuff before the focus and the stuff after the focus. So cursor returns the targeted element. Okay. Safe cursor start end moves the focus, I suppose. Okay. Yeah, I think that I would rather use this zipper than implement my own. It looks like they've done a lot of stuff that would be helpful. So I would like to add a dependency on list zipper, please, to my Cabal file. I guess I need to put a comma there. And we'll just say we want version greater than or equal to 0, 1.2.0, but less than 1.3.0. There we go. And now let's not define our own zipper at all. We'll just import data.list.zipper, and we'll just like import everything, I guess. Why not? The stuff they have here should not really conflict with anything, and if it does, we can hide them. Okay, so now we have a zip list, and all right, the idea is we're going to implement. Oh, sorry, you guys have to see this. Very funny. We have a data.list zipper, and I put this in the Cabal file. Nothing interesting happened. So what now? Well, we need to read the input, I suppose. So let's start with that. Main equals interact of part1 composed, show composed with part1 composed with, I guess we should go get our input would be a good idea. I won't bother showing you guys the browser here. I'll just download it and input.txt, yes, paste, there we go. So it's a single, a large number of instructions, of lines, each with one instruction. Fine. So how do we read that? We are going to call map read and on the result of calling lines, right? And read will take those strings that are on each line and convert them to positive or negative integers for us. So part one, actually, I should be a little more careful. What does it, where do we start? Do we start at the first instruction? Positive, the following. Here, I guess I thought this was going to be short, so I wasn't even going to bother showing you guys, but I don't actually see here. Clearly, like, because of the example, we're meant to start at the first one. But I don't actually see written in the prose here anything that tells me. Ah, here it is. Start at the first instruction in the list. I know Eric is quite careful to make this explicit, and I was surprised I couldn't find this, but okay, start at the first instruction. So, after we've called map read, we want to do one more thing, which is we have a list, but what we want is a zipper list, right? Where's my list zipper? There's, how do I make one of these things, please? To list, from list. So returns a zipper containing the elements of x's focused on the first element. That's perfect. That's exactly what we want. From list, like so. Yes. So now we just need to write a function. Part one is a function taking a zipper of int and producing as output an int. Simple enough. So what happens if you... All right, time to read the zipper documentation again. What happens if the cursor falls off the end? Left, right, delete. Not sure. Okay, well, we'll find out. In fact, let's try part 1 equals undefined. Sorry, I'll show you guys. Undefined. I need to change my keyboard shortcut for switching windows because it is a button that Emacs wants to do something with. So what I want to try now. Could not find this. Well, I feel as though you should have found it. I needed to turn on Intero mode. What is wrong, please? List zip. What? Following exceptions were encountered. List zip must match that. Has no specified version needed since it is a build target. What does this mean? I have no idea. Build failed, but trying GCI anyway. Cannot specify that. I don't have any idea how to, I really don't, how to use Haskell stack to, do things. I guess if I were a professional Haskell programmer, this would be very helpful to me. Make it very easy to just get packages and isolate them to a specific project or whatever. But, what package? I don't know. Contents? It seems like list zipper is what I want. Sorry, I'm back here now. The package seems to be called list zipper. And I want in my Cabal file, I say that I want, oh, it's called list zipper? I guess it's called list zipper, not list zip. Did I get that wrong? And also, yeah, okay. Does that help? So if I now say cannot satisfy package list zipper, I don't know why. Does it not, it's on Hackage, right? Would it be on, is it that it's not on Stackage? Haskell Stackage list zipper. So here's Stackage LTS. List zipper. No. So it doesn't exist in the world that Intero knows about. Okay. Zipper. Okay. Data text zipper, generic traversable zipper. None of these are actually really what I want. These are all way too generic. And I want just a list zipper. Because it's too complicated to do anything else. Oh, more results. Sigh. Yeah, we really don't want to deal with generics for this. There's a string zipper. We're close. Where is this? It's in text zipper. Why? Why isn't it more general than text? Any list. There's a tree zipper even, but I don't want that. Well, we can implement our own zipper, I guess. It's not like the most complicated thing in the world, and it's a good exercise, I suppose. Why is it not switching to show you guys a different... oh, because I forgot the window number. Okay. Blah. Okay, well, forget this stupid library. Get out of here. Go over to our Cabal file. Get rid of this thing at the bottom, too. And we're just going to define data zipper of A equals either an empty or a zipper of list of A, and list of A. So, right, we're storing a focus element and the stuff to the left or right of it, is the idea. And we will just have to do this ourselves. So, first question, we have to define a few useful features for a zipper, but we can do that. So first thing we need is left. Take the zipper A and produces maybe a zipper of A, but it might not if you fall off the end, is the idea. So left, we're never going to have an empty zipper, so I'm just not going to include that. And we're going to say it's a non-empty zipper. Left of zipper of an empty list, anything, whoops, equals nothing. You can't move left in a zipper where there are no elements to the left. You fall off at that point. Left of a zipper of a left list, which is an X and some more things, and whose focus element is Y, and whose right element we call ours, I guess, is equal to a new zipper whose left pointer is just X's without X on the front, whose focus element is X, and whose rightmost thing is Y const onto ours, right? That looks about right. And we'll do something similar for right. Oh, hang on, we have to return just that zipper. So maybe is a type which has, there's two different ways you can have a maybe value. You can have a nothing, or you can have just of some value. So this is sort of like Haskell's version of null, except that it's opt-in and explicit. It's not implicit. It's not like every value type can be nulled. You know, if you want to have the possibility of something be nothing, you have to make it a maybe type and say explicitly that you're willing to handle the possibility that it might be nothing. And the compiler is there to help you with that. So now we have right, which has this same type. Right of a zipper of anything over here and nothing on the right is nothing. And right of a zipper of lefts and Y and X's is just a new zipper of what? We moved right, so our new left should be Y const to L's. Our new focus should be X, and our new rightmost stuff should be X's. Great. So now we just want focus is a function that takes a zipper of A and produces an A. We say focus zipper of any left and X and any right is just X. And what else do we need? We need a probably modify function. So modify is a function from zipper. It takes an A to A and a zipper of A and produces a new zipper of A. Modify a zipper where the left value is anything. Yeah, a little more careful here. L X and R equals a new zipper with the same left. F is our function. F of X and R. So we'll use this to change what is in our zipper. So these are the like 4 basic functions that we'll need to work with a zipper, and I think that should really be it. I haven't implemented part 1 yet. We will also need a from list function that we said we were going to use, right? So from list is a function from a list of A to a zipper of A. And from list of an empty list is an error. We've said empty zippers are not allowed. This is sort of cheating. But we're just never going to do that. And from list of any other of a list whose first element is X and whose remaining elements are X's is equal to a new zipper with an empty left, a focus of X, and a right of X's. There we go. So now, in principle, this should at least type check, yes? Oh, we can't Intero mode is enabled. Intero, I should kill that Intero REPL buffer. How about now? Okay, it compiles. Great. I don't know what that warning is about, but I don't really care, I guess. Okay, so this all compiles, and now we can start writing a function that works with our zipper. But do we want to do that in this episode? I don't know. I guess. Why not? These are a bit longer than my gaming episodes, but I guess that's fine. I'm trying to work through the backlog of Advent of Code problems, so sure. So what do we do? How do we implement part 1? I think we will want a function which moves a zipper n times in a particular direction, right? Applies either the left or right function n times, stopping if it ever falls off the list to return, and will return nothing at that point. So let's write that now. It'll be useful to have. Move by is a function taking is move by a good name? Because I want to call it like move left 5 z, where z is my zipper. I think that's a useful order to call things in. Maybe even move z left 5? Move z 5 left? Which of these makes sense? I kind of like move z 5 left, although it seems really dumb. It just like is not gonna... I'm thinking about how it's going to feel to call that function, and it's just sort of like... in Haskell, you often want to put the arguments to a function that will change the most often. You put them sort of on the right, and the arguments that will change the least often, you put them on the left, and that sort of helps with partially applying things. And I think move left 5 is the best we can do, for that anyway. So this is a function that takes a function as its first argument, zipper A to maybe zipper A. And actually, we can be much more general than this. It doesn't even need to know it's working with zippers, just with some function that that might return a value of the same type and might not. So we can actually just say it's a function from A to maybe A. and an int, and an a. And it produces output a maybe a. This feels like something that might already be in the standard library, but I don't know exactly what it is. So it's probably like replicate m for the maybe monad or something crazy like that. I don't know. But so we'll just write this. Move f of 0 and x is equal to x. How do you apply a function 0 times to a value? Just return the value. Just x, I suppose. So this is sort of how you write recursive. This, I suppose, is the first time that we're trying to like perform an iterative process on a value by ourselves. In the first few exercises, we sort of worked with like mapping over a list and so on, and like doing list comprehensions. And so all the magic of like variables changing values sort of happened by itself, and it was sort of, it never felt like we needed mutation. But here we want to change a value like n times, right? It sort of feels natural to do that imperatively by just modifying a thing, which you can't do in Haskell. And so Haskell functions use recursion very heavily. It turns out that pretty much anything you could do with iteration, you can do with recursion instead. And it often turns out to be pretty clean. So we just define our base case here, which is move any function 0 times is equal to x, or just x. And otherwise, we say move f n of x equals let's say case, we can be fancy, right? Sure, we'll be a little fancy. Well, let us first call f of x. That's an obvious thing we want to do. And do I want to bind this exactly? Probably. Bind it to move f of n minus 1? Is that all? Yeah, that looks about right. Does it type check? It does. Intero process is not running. Why? Excuse me? Intero restart, please. Yeah. So move does type check and has this type. How nice. The type we wanted. So what's the deal with this funny little bind operator? It does a lot of fancy things. It's closely related to do that we saw earlier. But the idea basically for the specific case of maybes, it's more general than that, but for a maybe, it says take the value on the left, in this case f of x, and if that value is nothing, then just return nothing. Ignore the value on the right completely. Otherwise, the value on the right should be a function which will be called with the value inside of the maybe on the left. And then we just return that value. So that's, we're sort of letting Haskell and the bind operator handle all the weird fiddly bits of like checking whether the null value is null or not, sort of implicitly for us. So where we say, we have our base case, and we have just like use bind. Like try doing the recursive call of like move f of n minus 1, but like also if the thing on the left was nothing, then just give up early. And so like this may be a little bit magical. Like, does it work? Who can say? So let's say that we wanted to do this. Let's do a test. Like limited add. Limited inc, let's say, for increment of x. Actually, let's say limited dec of 0 equals nothing. You can't subtract 1 from 0, but otherwise limited dec of n equals limited dec equals just n minus 1. Very simple function. Limited I guess we have to give it a type. Limited dec takes an int and returns an int. Maybe int. Oh, I see. It was mad because I forgot to put the just here. Okay, we don't actually have to give this a type, right? Yeah, Haskell can figure that out. So let's say I do that, and I say, I want to move with limited dec 10 times from 100. We get back just 90. Yep, you can do that. But what if I said I wanted to move limited dec 10 times from 5? We get back nothing. Because after decrementing 5 times, it tried decrementing a 6th time and said, wait a minute, there's no longer an integer for us to work with. The function gave up and returned us nothing. And so the whole process just sort of aborts. We don't call limited dec any more times than that. So that's the idea. Like, I mean, maybe and bind are a little bit complicated, but it's really cool that we can write this fairly abstract and not super powerful, but it does some, like, it's really nice that it, like, we don't have to handle the nulls ourselves. They're just sort of handled for us, automatically bottomed out by this bind thing. And we don't even have to think about them. And now we can use that to implement our moving the zipper in a direction, right? So what we're going to do now is say part 1 of, let's call it a program, equals, well, equals what? Let's let amount equal the focus of the program. So look at the zipper and see what's in it and read that. And now let the new program be modify program with +1 to add 1 to the instruction we're currently looking at. And I guess we have to now take negative numbers. So we want to either move right a positive number of times or move left a positive number of times, depending on whether the value we're looking at is positive or negative. So we kind of need a dir and distance to be. If amount is less than 0, then the dir is left and the distance is how do I write that again? Minus dist, I think. Otherwise, it's equal to right and dist. So we read the focus, and then we compute from that how far to move in which direction. We compute a new program by modifying the current thing we're looking at, adding 1 to it. And finally, I guess, we need to be a little bit more careful by saying what? Part 1 equals actually go 0, because we need to track. We can't just be modifying like the program and tracking where we are. We also have to track how many jumps we've taken. So I'm going to say that we're defining a new helper function called go. This is sort of a typical Haskell thing to do, is use a helper function, and they're often called go, where you like pass some extra arguments to it that you didn't get in your part 1, but that you need for your recursion. So we can say that go, so part 1 will say start the program having jumped 0 times. Yeah. And I guess we'll actually just say go 1. It'll be a little more simpler. 1 will be what we initialize n to be. We've computed a new program from modifying the existing program. And now we will write an in. So we've let all of these values, and now we want a body of our let expression to be case move dir dist new program of and if that move resulted in nothing, then we should return n. That jump was the one that that escaped the maze for us. Otherwise, then it must have been just a new program, in which case we will return go n plus 1 of that new program. Why are you upset about this program? Oh, modify takes its arguments in the other order? Okay. Okay, this is sort of a lot of writing, but the good news is all of it sort of, I think, makes a reasonable amount of sense. And how confident am I that this works on the first try? Not very. A lot of Haskell programs, you know, there's a saying, if it compiles, it probably works. And, like, it's honestly, like, sort of true. A lot of the programs that I wrote for Advent of Code so far did work on the first try. In day 3, well, you saw day 4, that one was just a breeze. But in day 3, my part 1 solution did work the first time I ran it. Part 2 took quite a number of tries because I had not refactored correctly, and so I was just like doing some stuff that was totally wrong, but was still type correct. So anyway, I don't think we can do anything but try it at this point and see what we... I don't need my REPL, get out of here. See what we get. No, I've forgotten how to use tmux. Okay, so day 5, please. And let's try running GHC with the input. Okay, it's taking a long time, and this worries me a lot. Loop. Great. So this tells me very little. It just says somewhere I have an infinite loop, a value that refers to itself. Where? Unclear. But probably there is some function I have written that calls itself. And I guess now is the time to learn how to turn on more warnings. Because I bet that there is a warning that GHC could give me about exactly this problem that I have written. Because it's not like Haskell can't detect every infinite loop. It can only detect really dumb ones. Where like a value refers to itself and is not productive in the meantime. Here's what it is. We have... No? Yes! We have the definition of dist depends on dist itself, whereas I meant for it to depend on amount. You can define circular values in Haskell, values that refer to themselves. And we've done that many times already, actually. And it's useful to be able to do that, especially for functions, but also for some other things. And so it's not an error to do that, but it definitely is not what I meant. So let's try this. Hello? Any progress? On the one hand, we're not getting a loop. On the other, we don't have much visibility into whether the program is making any progress, right? It seems like we would probably be done by now if this were the correct answer. But I can always just leave it running in the background while I start looking at like what could be wrong. And possibly add some like debugging stuff to go on here. First of all, do these definitions look okay? Left looks, I think, fine. We peel the leftmost element off. We peel the rightmost element off of the left list and make that our new focus, and yeah, okay. Right looks okay. I think it's pretty much the same. Peel the leftmost element off the right list and make it our new focus. Add the old focus to the left side of the list, fine. Focus is obviously correct. Modify is obviously correct. From list. Yeah, hard to argue with. That's got to be correct. Move. That one is a little bit tricky, but we tested it with non-zippers and we found that it was correct, so I'm reasonably confident in this. So the problem must be here somewhere if there is one. We got an answer, actually. Okay, so cool. So let's try that. It was a little bit slower than I expected. That's the right answer. Okay, so it's just a kind of long program. Great. So aside from that loop that we had, it actually did work on the first try. How nice. Part 2. Now the jumps are even stranger. After each jump, if the offset was 3 or more, instead decrease it by 1. Otherwise, increase it by 1 as before. Okay, well that's very easy for us to fix because we have one place in our program where this change happens, and it's modify. So let's git add the stuff here and git commit day 5 part 1 and go look at how to make that change. Really, all we need to do is take this part of the function and make it a little bit more general, right? Make it an argument to the function. So what we're going to do is rename part 1 to solve. But it takes a function additionally from int to int as an argument. Solve f, and then we just modify with f here, right? So we'll say that part 1 equals solve of +1, and part 2 equals solve of... Dang it! Here's all the stuff I just did, guys! Excuse me, had a bit of a cough there still. So there was a +1 here. Actually, I can show you guys. I took this this +1 here, and I wanted to make it a function parameter. So I replaced it with f, and gave this function a new argument called f, and renamed the function from part 1 to solve, with the plan to define part 1 to be solve of +1, which is now like exactly the same as what the old part 1 was. We just defined a new function that produces solvers when given a function, and then we called it with the function that we were using before, and now we got the old solver that we used to have. And now we just need part 2 to be a solver that uses a slightly different function. And that's going to be very simple. And I just needed to look up what is this rule. If the offset was 3 or more, decrease it by 1, otherwise increase it. Okay, so that's easy. Solve f, where f of n, if n is... Gotta show you guys the code, here you go. Such a pain to remember that, sorry again. If the offset was 3 or more, so if the offset is greater than or equal to 3, then we return n minus 1. And otherwise, it is equal to n plus 1 as before. And so we can just write part 1 and part 2 here. Import control.arrow, like so. And I think that that's probably about it. Let's just run GHC again. And that'll take a while, especially since it's redoing part 1, which, yeah, I know we didn't have to do, but I like to have my programs, as I've said before, solve both parts, be a complete solution to the day. And so if part 1 were extremely slow and I didn't think my solution to part 2 were correct, I could temporarily edit this to remove the extraneous solution to part 1 and so on. So something that I would like to know about Tmux is, how can I tell when something has happened in my bash window? I believe there is a way to do that, but I thought that it would display a little indicator next to it, and it seemed to me that it didn't do that before when the thing finished. Notice, by the way, that I didn't bother giving types to part 1 and part 2. You don't have to, and they're quite simple, so why bother? And overall, I'm quite happy with, we ended up having to do a little bit of work to define this zipper, but it was a very, it gave me a chance to exercise what I know about zippers, and to show that I do understand how to use them, more or less. And we needed relatively few functions, and by writing modify and move, we built a couple of general tools that are useful for this problem, but also perhaps for some future problems. And modify ended up being exactly what we needed. If we had sort of hard-coded a 1 in here somewhere, a +1, then it would have been harder to do the +2, the part 2 thing. Yeah, so I don't know. Nothing appeared in my Tmux thing when that changed. I'm not sure how to make that happen. But so for our own comfort, 387.096, is that what we had before? Yes. So we haven't broken part 1 as a result of our generalization, which I think means that part 2 should be fine. I think. I don't know. I guess it could be broken, but it's a relatively simple thing, function to have written. So let me explain a little bit more carefully what the deal is with a zipper. So a zipper is a different way of thinking of a single list, where there is one element in the list that is sort of the one under your cursor, the one you're thinking of. And especially, it makes it much easier to modify or to produce a new zipper with that value modified, of course, since you can't modify things in Haskell. To modify a list and to give sort of, not exactly random access, but in a linked list, it's very expensive to change the last element. Especially in a purely functional linked list where you can't modify anything. If you have the linked list of numbers from 1 to 10, and you want to add an 11 to the end, you have to reconstruct the entire list from scratch. Adding a 0 to the front is very cheap, but adding something to the end is very expensive for these singly linked lists. Zippers solve this problem by keeping 3 values, which you can see in the data definition above. They keep an A, which is the current focus element you're looking at, and another list, which is all the stuff, a singly linked list of all the stuff to the right of there, and another singly linked list of all the stuff to the left of there, but backwards, so that it's cheap to add something to the front of that list, which is the rightmost of the reversed, the rightmost of the original list, which is the leftmost of the reversed list. So it's sort of a way to work with lists doing a sort of random access thing in this sort of more constrained fashion. And I'm glad that I was able to produce a zipper basically just out of my memory. All right, do we have any progress here? No. So there must be some much faster way of doing this. And I mean, obviously there is. We're building and tearing apart a ton of objects every time we modify a thing. If we had an array that we could mutate in place, this would be so fast. I think. But I don't know, like, there's just a large number of steps in this program too. Like, it would be a constant factor faster, but I don't think it would be a tremendous amount, like a huge quantum leap. And so this is, by the way, going to be the end of this episode. Over an hour, but at least we got, what, 3 problems done? 3, 4, and 5? We're getting close to caught up to live. Still running. Oh boy. So let's see. Maybe it would be interesting to describe bind and maybe a bit more while we're waiting. Sure. Let's look at the type signature of bind. Actually, let's look at the definition of maybe first, since it's sort of a form that we haven't really seen very much yet. Theta maybe of A equals nothing or just A. So, all right, we'll call it fake maybe, right? Oh, I see. Still running. So this is exactly how maybe is defined in Haskell, minus the apostrophes. It doesn't have to be a built-in thing like null does. It's just a, you know, you could define it yourself if it weren't in the standard library, and it would behave just as well. And we basically say a maybe is a polymorphic data type, a generic one, with one argument, an A. So you can have a maybe of int, a maybe of string, a maybe of list, of maybe, of zipper, of string, or whatever like crazy thing you want. Any type at all. And a value of type maybe A has 2 possibilities. It is either nothing, or it is a just containing an A. So that's how we have sort of this nullish thing, right? We say nothing is kind of like null. And there's a bunch of useful functions that can operate on maybes, sort of like ignoring the nothing case and returning nothing, or doing something else with it, like saying use a default value if it's nothing, and otherwise use the value that was in the just, or something like that. Killed? Why? Why would you kill me? What does that mean? Were you not making progress? What happened? What? I don't think I've ever seen something just say killed. That's very peculiar. Is there something wrong with my, with this? Okay. If the offset... Oh. I see. Hang on, wait a minute. Increase it. So... Well, so I was thinking for a moment that they might mean that, like, if the offset was -3 or more, then to still treat it as, to, like, make it smaller by turning it to -2, rather than, right, like, but I don't think that's what they mean. Because, yeah, that would just be crazy, and it wouldn't match what they say here. This -3 has been increased, not decreased. So that's not what we got wrong. That's very strange. I don't even know what causes Haskell to choose to kill a thing. Too much memory? Oh, I bet that's it. We're not being strict enough. And we're building up a huge, like, lazy list of stuff. Ugh, our zipper is not good enough. Ugh. Okay, well... So we could do this, I think. But we have to turn on bang patterns, basically? No. That actually just works. So what this is saying is normally Haskell is extremely lazy about what values it will compute. And so just because you write x plus 1 doesn't mean it will necessarily add 1 to x right away. It'll wait until someone needs the result of that expression before it actually does the computation. And this is quite nice because it means you can work with stuff like infinite lists. But there are times when it can be a problem if you are like building up a very large sort of pile of deferred work that you're going to eventually refer to, or that you might in fact never refer to. And so you can tell Haskell to be more strict in a number of ways, one of which is these bang patterns, where you say, I want a strict list of A, and a strict A, and a strict list of A. So that might help. And I want to try first just solve part 1 again and see... Did this make things any faster? Does it still work with those bang patterns in? I could compile with optimizations. That would probably help. Maybe. But I think that, like, it would make things faster, for sure. But I don't know that going faster is what's going to fix our problem. Our problem is that we have, like, bad memory management, right? And we're, I think, keeping a very large list of deferred work, probably. If I had to guess. We're bouncing around back and forth in the middle of the program and, like, not going all the way to the left or all the way to the right, and so we've built up a huge pile of deferred changes to the list on the left side or something like that. I don't know. Okay, well, I think that just sitting here watching this is not very interesting footage. And so I'm just going to go ahead and end this episode and continue tracking down the space leak that it appears that I have. If these bang patterns fix it, then great. At any rate, I'll let you guys know what happens in the next episode. And I'll show you the answer and so on. But just this sort of long debugging process where we're not even really doing much thinking, we're just sort of trying out answers is like not that much fun. So anyway, I guess that means we're done, right? Yeah. Thanks for watching, and I will see you next time.